The universe is expanding, but into what, if space itself keeps stretching what lies beyond its edge? Tonight we'll explore one of the most mind-bending questions in all of science. If you enjoy cosmic mysteries, please like, subscribe and share, and tell us in the comments, what do you think lies beyond the universe? Thank you for watching. Now let's begin. A quiet sky map unfolds as a catalogue rather than a spectacle, with galaxies rendered as small points, whose brightness and spectra are measured with care. Within each spectrum, narrow dark lines mark where particular atoms absorb light, and when those patterns are compared with the same lines measured in laboratories on Earth, the lines in distant galaxies sit to the red side. The shift is not random. Across directions on the sky and across many kinds of galaxies, it grows in step with indicators of distance. This simple visual fact, repeated over and over by different instruments and different surveys, becomes the first calm statement about the large-scale behavior of the cosmos. The pattern is not a single discovery pinned to a single night. It is a cumulative picture built from years of patient measurement, and it begins the story by showing what the data look like before any deeper interpretation. Distance in astronomy is inferred rather than carried by a ruler, so the foundation rests on a chain of linked methods. Nearby stars provide the first geometric baseline through their tiny yearly shift, against the distant background a motion called parallax that depends only on the changing vantage point of Earth round the Sun. From those anchors, relationships between the period and brightness of certain pulsating stars allow greater reaches to be measured, because their observed period tells their true brightness, and the difference between true and apparent brightness gives a distance. In galaxies that host both these pulsating stars and other indicators, cross-checks link one rung of the ladder to the next. Bright stellar explosions of a well-behaved kind provide another rung because their light curves follow patterns that can be standardized. Each rung is tested against the others, and the chain is refined across many independent datasets, so that the axis labeled distance on a plot reflects layers of careful calibration rather than a single assumption. On the spectral side, the redshift itself is measured in a grounded way. The same atomic transitions that appear in laboratories define unshifted wavelengths, while distant galaxies provide the shifted counterparts. The difference between them expressed as a ratio to the unshifted value gives a dimensionless number that captures how much the light has been stretched between emission and observation. When observers place distance on one axis and redshift on the other, the points do not form a scattered cloud. They align along a rising trend. Nearby galaxies show small shifts and correspondingly small inferred recession rates, while more distant galaxies show larger shifts and larger inferred rates. The line is not perfect because galaxies also move within their groups and clusters under local gravity, but the underlying trend remains. The first feeling the map gives is regularity. It looks smooth when averaged over enough galaxies, as if the same quiet rule holds in many directions at once. Three-dimensional maps provide a second window onto the same pattern. Modern surveys record angles and redshifts for huge numbers of galaxies across wide regions of the sky-building positions, with two angular coordinates and one redshift coordinate. Clusters appear as knots filaments thread between them, and wide underdense regions open like cavities. When the map is sliced into shells of similar redshift, the statistical properties of the galaxy distribution from shell to shell are remarkably alike. The texture of knots and filaments repeats, while the characteristic scale of structure remains similar after accounting for the changing depth. This repetition supports the idea that the trend is not an accident of one patch of sky or one special set of galaxies. It suggests that the large-scale universe, when smoothed over the restless details of clusters and groups, behaves the same in many directions, a property that allows a single relation to summarize the data. If the trend is real and global, a simple summary should capture it, and observers do find such a summary. The present-day proportionality between the apparent recession rate of a galaxy and its distance becomes a single number that characterizes the current expansion. Nearby galaxies appear to recede more slowly, and more distant galaxies appear to recede more quickly, so the ratio of recession rate to distance settles toward a nearly constant value for modest distances. Different teams infer this value by different combinations of distance indicators and modelling choices, and they report careful uncertainties as part of the result. The details of inference will be explored later, but for the moment the point is descriptive. A single number captures a snapshot of the expansion today, and the data that deliver it are visible on the simple redshift distance plot. The idea of recession in this context needs careful language. A spectrum records light that departed long ago and arrives now, so the redshift does not report a present speed in the way a speedometer reports the speed of a car at a moment. Instead, it records how much the wavelength has been stretched during the entire journey. Two observers located in remote galaxies can each see the other's light shifted to the red without contradiction, because both participate in a common large-scale behavior rather than moving through a fixed background in opposite ways. This symmetry is already visible in the data. The relation looks the same when averaged over enough galaxies from many vantage points, and it is this sameness rather than any claim of privilege for the Milky Way that the maps express. The data also show how local motions sit on top of the global trend. Within groups and clusters, gravity pulls galaxies around in orbits and flows. These motions add scatter to the neat line of redshift against distance. The nearest large cluster exerts a pull on nearby galaxies and on the Milky Way, nudging some points away from the straight relation. Observers correct for such motions statistically by using larger volumes, by mapping flows in the local region, and by combining many independent patches of sky. As the sample extends to greater distances, the irregular pushes from local gravity tend to average out, and the smooth relation grows clearer. The cautious statement that follows from all of this remains deliberately modest. Redshift data assembled over many years with many instruments arranged on the sky in deep catalogues, and three-dimensional maps show a smooth relation with distance. The relation is interpreted as evidence that on the larger scales the universe expands. This starting point does not yet require a detailed mechanism or an answer to the title question. It simply reports that light from distant galaxies is stretched in a systematic way that grows with distance, and that the pattern looks the same in many directions. The next steps taken slowly will move from this description to the framework that explains the trend without invoking motion through an outside space, but the calm foundation is already set by what the data look like. The map of redshifts invites an everyday reading in terms of motion, because in daily experience a siren's pitch drops as the source moves away and rises as it approaches an effect described as the Doppler shift. In a calm laboratory, light from a moving atom also shifts in wavelength in a way that records that motion. It is natural to extend this picture to galaxies, and to imagine each galaxy moving through a static background, its light reddened because it flees through space. The data, however, become more coherent and more symmetric when another description is adopted, one that comes from general relativity, and treats space and time together as a single geometry that can change with time. In this framework, the redshift of distant galaxies is not primarily read as the mark of motion through a fixed stage. Instead, it is read as a measure of how the stage itself stretches during the long journey of the light. The difference between these two views is not an argument of words, but a distinction in how distances and times are defined, compared and transported across large scales. General relativity allows any small region to look locally like the familiar flat space and steady time of everyday physics, but it also allows the larger region to curve and to evolve. In a small neighborhood around a galaxy, observers can speak of ordinary speeds and of Doppler shifts in the usual way, and those statements hold to excellent approximation. Over cosmological distances, however, there is no single global meaning for speed that every observer shares, because clocks and rulers at far separated points cannot be compared by simply sliding them together across unchanging space. To compare them, one must transport them through the evolving geometry, and that transport depends on how the geometry changes. The language of metric expansion captures this situation. A metric is the rulebook that tells how to compute spatial distances and time intervals from small coordinate steps. In the widely used large-scale model of the cosmos, that rulebook has a simple form whose key moving part is a single function of time that multiplies all the spatial pieces. When that function grows, the spatial distances between markers that ride with the flow of the cosmic matter also grow. These markers do not move through space the way a car drives down a road. They remain at fixed moving locations, and the distance between them changes because the rule for distance changes in time. Light that passes between those markers experiences the same change. Its peaks and troughs are carried by the geometry from the moment of emission to the moment of reception, and the distance between peaks stretches along with the distance between the markers. The observed redshift is therefore a record of the accumulated stretch of the wavelength, which in turn reflects the accumulated growth of the scale that measures spatial intervals. In this telling, there is no need to imagine a galaxy hurtling through a stationary void. Both the emitter and the observer are nearly at rest with respect to the average flow defined by the matter and the radiation in the universe, and the light is reddened because the distance between successive crests has been stretched by the evolving metric during flight. The Doppler picture is not wrong within a narrow patch where space-time curvature and time evolution can be neglected. In that local patch, one may transform to a frame in which the nearby region looks flat and still identify a relative speed, and relate a small redshift to that speed. Indeed, for sources that are not very distant, this local picture and the cosmological picture coincide in their leading behavior, and either language will fit the data to the precision required. The difference grows as the distances and the look-back times grow. When light has crossed a significant fraction of the observable cosmos, the accumulated effect of the geometric stretch dominates the measurement, and the cleanest language is the language of metric expansion. A second effect, gravitational redshift, further clarifies the distinction. Light that climbs out of a strong gravitational well loses energy and arrives with a longer wavelength, a change produced not by motion through space, but by the difference in gravitational potential between emission and reception. This effect, well measured near massive bodies, is described by the same overarching geometry that describes metric expansion. In both cases, space and time together determine how frequencies and wavelengths change. The Doppler story remains useful as a gentle doorway because it connects to everyday sense, but the full account rests on how clocks tick, and rulers measure when the geometry is not static. Observers often ask whether two different processes are at work in the same beam of light, one part Doppler from motion, and one part cosmological from expansion. In the geometric view, this separation is not required and not unique. One can always choose a local description in which a small Doppler piece accounts for the shift over a short segment of the path, then compose many such segments along the route. The composition of many local Doppler steps across an evolving geometry is simply another way of writing the single accumulated stretch encoded by the metric. Both languages describe the same physical evolution of the wave, but the metric language does so without introducing a preferred frame or a global speed, which the large-scale cosmos does not supply. The symmetry of the observation supports this. Two observers on distant galaxies, each riding the overall flow, each see the other's light shifted to the red by similar amounts, determined by their separation and by the shared expansion history. No contradiction appears because no claim of motion through a fixed background has been made. The redness is a mutual record of how much the geometry has grown while the light travelled. The same symmetry helps explain why nearby peculiar motions create scatter without erasing the trend. Random local velocities superimpose small Doppler shifts that can blue shift or red shift light by modest amounts. But as one looks farther, those uncorrelated motions tend to cancel when averaged, and the common geometric stretch stands out. The practical use of this understanding becomes clear in how observers infer the expansion history. When a redshift is paired with a distance indicator, the pair is interpreted through a model in which the scale that measures spatial intervals changes smoothly with cosmic time, according to equations that couple the expansion to the contents of the universe. In this interpretation, the present proportionality between recession rate and distance is not just a rule of motion, but a manifestation of the current rate at which the scale grows. When the same logic is applied across a wide range of redshifts using diverse distance indicators, the result is a reconstruction of how the scale has changed over time, not a map of how galaxies have flown through a static space. The language matters because it prevents confusion about what the universe is doing. If one imagines galaxies speeding away through pre-existing emptiness, a question about what medium they move through and what edges they approach naturally arises. If one instead recognizes that the measurable separations between comoving markers grow because the metric changes, then the need for an outside medium falls away. The change is intrinsic to the geometry, and the correct questions move toward how that change is governed by the contents of the cosmos and how it is measured by light. With that shift in language, the next step can build the simple symmetric model of the large-scale universe that makes these statements precise. But for the moment, the distinction stands. Doppler language suffices locally, while the calm description that unifies the data across the sky is metric expansion. The calm framework that gathers the descriptive facts into a single picture is the Friedmann-Lemaitre-Robertson-Walker model, which treats the large-scale cosmos as a space-time with simple symmetries. The guiding idea is called the cosmological principle, a statement that when one smooths over the restless detail of galaxies, clusters, and filaments, the universe looks the same in all directions and at all locations. This is not a claim about every small region. It is a statement about an average taken over large scales, and it is supported by the near-uniform glow of the cosmic microwave background and by galaxy surveys whose statistical properties repeat from one wide patch of sky to another. With this principle in place, space-time is built by choosing spatial slices that are each homogeneous and isotropic. Homogeneous means that no location is singled out by the laws of distance on that slice. Isotropic means that no direction is privileged. Mathematicians know that there are only three families of such spaces, one with positive spatial curvature, one with zero spatial curvature, and one with negative spatial curvature. Those three options may be pictured loosely as spherical, flat, and hyperbolic. The Friedmann-Lemaitre-Robertson-Walker model allows any one of these geometries for each moment of cosmic time, and then lets the overall scale of that geometry change with time in the simplest possible way. The machinery that accomplishes this is the metric, the rule that converts tiny changes in time and space into measurable intervals. Because the spatial part is homogeneous and isotropic, it must have one common scale that multiplies all spatial distances at a given time. That common scale is the scale factor. When the scale factor grows, the proper distance between markers that ride with the average cosmic flow grows in proportion. When the scale factor shrinks in the early chapters of cosmic history, those same distances shrink. A single function of time therefore captures the stretching pattern that maps directly onto the redshift trend described earlier. The temporal part of the metric introduces a preferred slicing called cosmic time, clocks that are carried by observers who move with the average matter and radiation content of the universe, and who feel no local forces tick in step with cosmic time. This choice is natural because it ties the passage of time to the average flow defined by the contents of the cosmos rather than to any one local motion. In these coordinates, galaxies that simply follow the flow have fixed co-moving positions, and their changing separations are accounted for by the changing scale factor rather than by motion through space. The power of the Friedmann-Lemaitre-Robertson-Walker model is that these few ingredients are enough to connect geometry with physics. General relativity supplies equations that tie the rate at which the scale factor changes to the types and amounts of energy and matter present. In words, curvature in space-time is linked to energy and pressure. When the contents are described on large scales by a nearly uniform mixture of matter radiation and a possible constant energy density of the vacuum, the time evolution of the scale factor becomes a smooth function that can be inferred from observations. Because the metric is so symmetric, light paths and distance measures can be written down without complicated detail. Light follows trajectories that always travel at the same speed with respect to the metric, and in this homogeneous and isotropic setting, those paths are simple curves that connect emission and observation along the evolving spatial slices. The stretching of a light is then nothing more than the ratio of the scale factor at reception to the scale factor at emission. Although the model is simple, it is not fragile. Small departures from exact homogeneity and exact isotropy can be laid on top of it as perturbations. Those small ripples describe the seeds of structure that later grow into galaxies and clusters, while the background continues to follow the smooth rules. This separation is what allows one to talk cleanly about a large-scale expansion while also acknowledging the complex local motions in clusters and filaments. The signs that support this separation are visible in the near uniformity of the cosmic microwave background temperature across the sky, and in the statistical sameness of galaxy clustering across very large volumes. The Friedmann-Lemaitre-Robertson-Walker model also clarifies the language of curvature and shape. Spatial curvature describes how the geometry bends within each constant time slice. Positive curvature implies that the sum of angles in a large triangle drawn by geodesics on that slice exceeds the familiar value from flat geometry. Negative curvature implies that the sum falls short. Zero curvature preserves the familiar value. Shape in the sense of global topology is a separate question. One may have a flat geometry that is infinite, or a flat geometry that repeats so that it is finite without an edge. The same is true for the positively curved and negatively curved families where multiple topologies are possible. Observations constrain curvature tightly near the flat case, but they do not fully fix topology. The model therefore keeps geometry and shape distinct, and it lets observations push on both. Another strength of the model lies in the clean definition of distance measures. The proper distance between co-moving markers at a moment of cosmic time is the scale factor multiplied by the co-moving separation. The distance that relates observed brightness to known luminosity is called the luminosity distance. and the distance that relates observed angular size to known physical size is called the angular diameter distance. In a curved and evolving geometry, these distances are not the same function of redshift. Their differences hold information that helps pin down curvature and the time history of the scale factor. Thus, the model explains why multiple independent observational strategies are valuable rather than redundant. The simplicity of the Friedman-Lemaitre-Robertson-Walker model does not mean that every subtlety is solved within it. It is an approximation in which the universe at large is smoothed into an almost perfect fluid with well-defined average properties. Questions about how small-scale clumping might in principle feed back into the average expansion have been examined carefully. The consensus from many studies is that such back-reaction effects are small for realistic levels of inhomogeneity, so that the simple background evolution remains an excellent description. The model also assumes a single cosmic time that is meaningful on large scales. This is allowed by the same near uniformity that the observations show. In strongly inhomogeneous settings, defining such a global time is more delicate, but on cosmic scales the near uniform glow of the microwave background and the statistical symmetry of large surveys defend the choice. Equipped with the Friedman, Lemaitre, Robertson, Walker metric, one can now speak precisely about what expands and at what rate. What expands is the scale that converts co-moving separations into proper distances on each slice of cosmic time. The rate is the time derivative of that scale expressed relative to the scale itself, a quantity that present-day measurements infer from redshift distance relations. Nowhere in this construction does the model call for space to move into an outside. The change is internal to the rule of distance and time within the geometry. Coordinates can be chosen in many ways, but the physical content is the same. Moving markers keep their labels while their proper separations evolve. Light accumulates a stretch equal to the growth of the scale between emission and reception, and the curvature of each spatial slice is either positive zero or negative, with observations indicating a value close to zero. The outcome is a gentle but powerful picture in which a handful of symmetries and a single time-dependent scale describe the large-scale behavior of the cosmos. From this picture, the observational relations of the first sections find a natural seat, and the later questions about curvature topology and acceleration acquire a clear language in which to be asked and answered. The scale factor is the quiet heart of the large-scale description, a time-dependent ruler that tells how far apart comoving markers are on each slice of cosmic time. A comoving marker is an imagined point that rides with the average cosmic matter and radiation, not chasing local motions and not drifting against the overall flow. Two such markers have a fixed co-moving separation by definition, and their proper distance at any moment of cosmic time is given by the scale factor at that moment multiplied by that fixed separation. When the scale factor grows, proper distances between co-moving markers grow in step. When the scale factor was smaller in the past, those distances were smaller. Nothing in this statement requires motion through an outside space because the change happens within the rule for distance itself, which is what the metric provides. The phrase cosmic time carries a precise meaning here. It is the time measured by clocks that ride along with the average flow and that feel no local forces. In practice, one can imagine a family of ideal observers who all see the faint microwave background as nearly the same in every direction. Those observers define a preferred state of rest for the large-scale universe, and their synchronized clocks define cosmic time. This choice of time is not a guess. It is singled out by the near uniformity of the microwave background, which makes clear that there is a natural notion of being at rest with respect to the overall contents. With cosmic time in place, one can picture the evolution as a sequence of spatial slices, each slice labelled by a single time, and each slice carrying a single scale factor that multiplies its spatial distances. Because the scale factor is only defined up to an overall constant, a convention is adopted to fix that constant. The present value of the scale factor is set to 1 by definition. This is not a measurement, but a convenient choice of units, like deciding that the current day on a calendar is called day 0. With that choice, all earlier times have a scale factor less than 1, and all future times, if expansion continues, have a scale factor greater than 1. The redshift of light slots naturally into this language. A beam of light that leaves an emitter when the scale factor has some earlier value and reaches an observer when the scale factor has a later value arrives with its wavelength stretched by the same ratio as the scale factor has grown. The observed reddening therefore tells how much the scale has changed between emission and reception. This is why the map of redshift and distance is a map of the history of the scale factor rather than a map of speeds through space. When a standard candle with known luminosity is seen at a given redshift, its dimness tells how far the light has travelled within the evolving geometry, which depends on how quickly the scale factor grew along the route. When a standard ruler of known physical size is seen at a given redshift, its apparent angular size tells how the geometry has expanded and how space is curved. In both cases, the scale factor is the time-dependent ruler that must be integrated across the light path to connect emission and observation. The rate at which the scale factor changes carries special meaning. If one takes the time derivative of the scale factor and divides by the scale factor itself, the result is a rate with the dimensions of 1 over time. This present day rate is the same constant that appears in the proportional relation between recession speed and distance for nearby galaxies. Observers infer it by pairing redshifts with distances and by fitting the relation in the local universe, and they refine it by using many independent anchors across the distance ladder. The value is not guessed but measured, and it carries an uncertainty that reflects the calibration chain. The same rate appears inside the smooth equations that tie the expansion to the energy and pressure of the cosmic contents. Those equations say in words that more matter and radiation tend to slow the growth of the scale factor through their gravity, while a uniform energy density of the vacuum tends to accelerate the growth. Whether the scale factor speeds up or slows down at any epoch depends on the balance among those ingredients. This dependence turns the scale factor into a historical record of what fills the cosmos. In the early universe, when radiation carried more energy density than matter, the scale factor grew in a way that reflected the strong influence of radiation pressure. Later, as matter became dominant, the expansion slowed compared with that earlier time. In recent cosmic time, the data point toward a gentle acceleration, driven by an energy density that does not dilute as space expands, which is consistent with a cosmological constant. None of these statements require writing formulas to make their content clear. They are statements about how the time-dependent ruler responds to what is in the universe. The scale factor also provides a clean way to talk about ages and durations. The age of the universe at the present moment is the time since the scale factor was effectively 0 in the simple backward continuation of the model, a limit that indicates a hot, dense early phase rather than a literal point in ordinary space. Look-back time to a given redshift is the difference in cosmic time between now and the time when the scale factor had the smaller value that produced that redshift. Distances that matter for observation, such as the brightness distance and the angular diameter distance, are integrals of the scale factor history along the light path. Without the scale factor, these ideas would float without anchor. With it, they become well-posed questions that the data can answer, because the scale factor multiplies all spatial distances on each slice. It treats every comoving separation the same way. This uniformity is what allows two distant observers who both ride with the flow to agree on the large-scale picture, even though they are far apart. Each sees the other's galaxy redshifted by an amount that depends on their separation and the shared expansion history. Each can assign a cosmic time to events by using clocks that are calibrated to the same microwave background rest frame. The scale factor underwrites this shared language. It does not care about local motions within clusters or about the details of individual galaxies. Those local details ride on top of the smooth evolution as small ripples. A practical worry sometimes arises about whether small-scale clumping could change the average growth of the scale factor in an important way. Detailed studies that model the universe as a nearly uniform fluid with small perturbations find that the feedback from clumping onto the average expansion is very small for realistic levels of inhomogeneity. The smooth background description remains an excellent approximation, and the scale factor remains the correct ruler for the large-scale dynamics. Another point of language concerns what is and is not being claimed when one says that distances expand. The statement applies to separations between co-moving markers, not to the sizes of systems that are held together by their own gravity or other forces. A bound galaxy does not swell as the scale factor grows because the internal forces that hold it together define their own local balance that decouples from the gentle, large-scale stretch. Planetary systems and atoms are even more strongly bound and are not stretched by the cosmic expansion in any meaningful way. The scale factor speaks to the geometry in which those bound systems are embedded, not to their internal sizes. Finally, the choice to set the present scale factor to 1 is a reminder that the scale factor is a relative measure, not an absolute meter stick. Only ratios of the scale factor at different times carry physical meaning. Those ratios are measured by the redshifts of light, and by the way distances inferred from brightness or angular size depend on redshift. When the data are brought together across many redshifts and many methods, the result is a reconstruction of the curve of the scale factor with time, and from that curve one reads the calm story of the large-scale universe. The scale factor is thus both a definition and a measured history, a simple multiplying function that turns comoving separations into proper distances, and a record that observers extract from light. It is the ruler that expands or contracts within the geometry, the clock that keeps cosmic time company, and the bridge that turns maps of galaxies and patterns in ancient light into a single coherent timeline of how the cosmos grows. Comoving coordinates provide a gentle way to label positions so that the labels do not drift while the large-scale geometry evolves. A comoving coordinate is a fixed tag attached to a marker that rides with the average cosmic flow, the same imagined markers used earlier to define separations that change only because the scale factor changes. In this language, each galaxy that simply follows the flow keeps the same comoving label even as its proper distance from other such galaxies grows with the scale factor. The separation that an observer would measure with rulers laid out at one moment of cosmic time is called the proper distance, and it equals the scale factor at that time multiplied by the fixed comoving separation. This split between fixed labels and changing measured distances turns out to be more than a convenience. It is the quiet backbone of how observations are organized and compared across time. Because the labels are fixed, a single three-dimensional map in comoving coordinates can hold galaxies seen at different redshifts and can be compared directly with theoretical predictions for the distribution of matter. The same separation between neighbouring labels means the same physical spacing at any time once the scale factor for that time is supplied. In practice, observers do not place markers by hand. They infer co-moving positions from angles on the sky and from measured redshifts translated through an assumed expansion history. The redshift gives an integral of the scale factor history along the path of the light, and when a model of that history is adopted, an estimated comoving distance follows. Angles on the sky then convert to comoving transverse separations through the same model. This dependence on the expansion history is not a flaw. It is the very signal that cosmological surveys seek, because the way that apparent sizes and apparent separations change with redshift encodes the time evolution of the scale factor and the spatial curvature. Comoving coordinates also help make sense of number counts and densities. If galaxies do not form or disappear in large numbers within a given volume, then the number of galaxies inside a comoving volume stays roughly the same over long times. The proper number density within that region changes because the proper volume grows with the scale factor, but the comoving number density remains more nearly constant. The difference is not subtle bookkeeping. It clarifies what is being compared when surveys at different redshifts report the abundance of objects. A count expressed per unit comoving volume can be compared across time without carrying a factor for the changing size of space. When a real survey must correct for selection effects, dust or detection thresholds, those corrections are applied on top of this clean geometric baseline. The same language relates to the pattern of clustering on large scales. The statistical measures used to describe galaxy clustering, such as the two-point correlation function or the power spectrum, are most transparent when written in comoving coordinates, because the comoving separation between any pair of points has a simple meaning that does not itself evolve. In this frame, a standard ruler like the preferred separation imprinted by sound waves in the early plasma appears as a fixed comoving scale that can be measured at many redshifts. The fact that this feature sits at nearly the same comoving length across cosmic time is one of the reasons it serves as a reliable probe of the expansion history. Observers do not live in a perfectly comoving world, and the departures are themselves instructive. Galaxies within clusters have peculiar velocities, motions with respect to the average flow that are driven by local gravity. These velocities add small Doppler contributions to the redshift and distort the apparent positions when a redshift is converted to a comoving distance by assuming pure expansion. On small scales, this creates elongated structures in redshift space, often described as fingers that point toward the observer when clusters are mapped. On larger scales, coherent infall into overdense regions creates a small flattening along the line of sight. These effects are not nuisances only. They carry information about how quickly structures grow and about how matter moves under gravity. Cosmologists model these distortions carefully and separate them from the geometric signal of the expansion. The fact that both the distortions and the geometry are described within the same overall framework helps keep the analysis coherent. Comoving coordinates also guide language about horizons. The particle horizon, which marks the largest comoving distance from which light has had time to reach an observer since the hot, dense early phase, is cleanly defined as a comoving radius. The event horizon, which marks the largest comoving distance from which light emitted, now will ever reach the observer in the far future if acceleration continues, is also defined in comoving terms. The use of comoving coordinates keeps these definitions from mixing the intrinsic growth of space with the labels that identify where events happen. In this way, the most global limits on what can be seen and what can be influenced become statements about the geometry and its time history, rather than about motion through a static backdrop. Another practical role for co-moving coordinates appears in the way simulated universes are built and compared with data. Numerical simulations that model the growth of structure under gravity place their particles or fluid elements on a co-moving grid. The grid stays fixed while the code tracks how small perturbations grow into the web of filaments and clusters. Forces and motions are computed in a way that separates the smooth background expansion from the local departures that create bound structures. Because the grid is co-moving, the large-scale drift driven by the scale factor is factored out, and the remaining motions speak directly to the physics of structure formation. When observers compare a galaxy survey with a simulation, both are most naturally expressed in co-moving units, and the match or mismatch between patterns can be read without first undoing a changing unit of length. There is also an everyday implication for the language used in public explanations. When a statement is made that space itself expands, one might worry that familiar objects should stretch as well. The co-moving framework shows why that worry is misplaced. A bound object like a star, a planetary system or an atom does not ride the co-moving grid freely. It sits in a pocket of space-time where local forces dominate, and its internal balance sets a size that does not track the scale factor. Only when forces are negligible and gravity from local inhomogeneities is weak do the co-moving markers provide the right picture. In that regime, the co-moving labels glide with the average flow and the proper distances between them grow with the scale factor. The co-moving approach also streamlines the discussion of cosmic time and simultaneity. Events that occur at the same cosmic time on different co-moving world lines are simultaneous within the large-scale slicing picked out by the near-uniform microwave background. This does not erase the relativity of simultaneity in general, but it provides a natural observationally anchored notion of simultaneous slices that is suited to cosmology. This shared slicing is what allows a map to be drawn with a label for the present and nested shells of earlier times marked by higher redshifts, each shell filled with co-moving coordinates that do not slide as time passes. A further use arises in geometric tests that compare radial and transverse scaling. When a feature of known co-moving size is measured along the line of sight and across the sky at the same redshift, any mismatch between the inferred radial and transverse co-moving lengths signals that the assumed expansion history or curvature is off. This purely geometric idea, often summarized as comparing shapes without relying on evolution, gains its clarity from the use of fixed co-moving rulers. It is another quiet way in which co-moving coordinates take a hidden supportive role in extracting the properties of the cosmic geometry from data. Throughout these uses, co-moving coordinates are not claimed to be the only useful labels. Other coordinate choices can describe the same physics. The virtue of the co-moving choice is its calm alignment with the symmetries of the large-scale model and its practical match to the way that light carries information through an evolving space-time. With fixed labels for positions that follow the average flow with proper distances that are simple multiples of the scale factor, and with a clean separation between background expansion and local motion, the ordinary tasks of counting, mapping, and measuring become transparent. In that transparency, the intuitive but misleading picture of galaxies racing through a pre-existing void gives way to a more precise picture in which the rule of distance evolves while the labels stay put. The co-moving framework thus ties the descriptive sky of the first section to the explanatory machinery of the next ones, and provides the stable stage on which the changing scale factor writes the history that observations can read. The present-day relation between apparent recession rate and distance is a calm summary of many measurements, and it is known as the Hubble-Lemaitre relation. It states that for relatively nearby galaxies, the rate at which they appear to recede grows in direct proportion to their distance. This statement is not a law imposed in advance. It is an empirical pattern that emerges when redshifts are paired with distances on a plot. The line through those points has a slope that can be read as a single number at the present time, and that number becomes a practical way to express the current growth rate of the scale factor. Because the relation is a snapshot, not a statement about all times, it must be inferred with care, and the steps taken to isolate it illustrate how observation and interpretation are woven together. The first step is to measure redshift with precision. Spectrographs record the positions of known absorption or emission lines in the light from a galaxy, and those positions are compared with their measured values in laboratories on Earth. The ratio of the shift to the laboratory value gives a dimensionless redshift for each galaxy. This part of the process is robust because it relies on atomic physics that is well understood, and because spectrographs can measure wavelengths with great accuracy. The second step is to infer distance. That step is more delicate because there is no single direct ruler that reaches out to other galaxies. Instead, a chain of methods ties near and far into one scale. Parallax measures distances to nearby stars through their small yearly shifts across the sky. Certain types of pulsating stars reveal their true brightness through a relation between period and luminosity, and when those stars are found in nearby galaxies, their observed faintness gives a distance. Supernovae of a specific type, when corrected by the shape of their light curves, provide bright standard candles that are visible across large distances. Each link in this chain is tested and cross-checked, and each link carries an uncertainty. The strength of the Hubble-Lemaitre relation lies in the way many such links converge on a consistent pattern when a large sample of galaxies and supernovae is considered together. One must also account for local motions that are superimposed on the global trend. Galaxies within clusters move under their shared gravity in ways that add small Doppler shifts to the pure cosmological redshift. Nearby structures can tug on galaxies and on the Milky Way, creating flows that perturb the simple linear picture at small distances. Observers mitigate these effects by choosing galaxies beyond the distances where local, peculiar motions dominate by averaging over large areas of the sky, and by modelling the local flow field to correct individual measurements where possible. When these precautions are taken, the relation between recession rate and distance for nearby objects settles into a clear line. The slope of that line is the present-day expansion rate. Its value is not a universal constant like the charge of the electron. It is a time-dependent quantity that happens to take a particular value now, and that value has been measured by multiple independent strategies. One family of strategies is anchored in the distance ladder described above. In that approach, nearby calibrators fix the absolute brightness of the standard candles found in more distant galaxies, and those candles define the line of recession rate against distance. Another family of strategies uses the imprint of early universe physics to set an absolute scale that can be projected forward to the present. The cosmic microwave background encodes a characteristic angular scale in its pattern of hot and cold spots, and galaxy clustering carries a characteristic comoving separation that acts as a standard ruler. When those features are interpreted within the same framework that ties geometry to contents, they imply a present expansion rate that can be compared with the ladder-based result. The broad picture is that a simple linear relation holds at modest distances, that its slope today can be measured, and that several routes to that slope exist. The routes agree on the existence of the relation and on the overall scale of the expansion, while careful work continues to refine the exact value and to check for unrecognized systematic effects in each method. The important point for the present narrative is not the pursuit of a specific number, but the role the relation plays as a local approximation to the evolving scale factor. Over short look-back times, the change in the scale factor can be approximated as linear in time, and the proportionality between recession rate and distance follows. Over longer look-back times, the simple line bends because the growth of the scale factor speeds up or slows down depending on the balance of matter radiation and any vacuum energy. Thus, the straight line one draws through nearby points is a calm first-order description of a curve that the full model traces across cosmic time. The Hubble-Lemaitre relation also carries a conceptual lesson that supports the metric view. The proportionality depends only on distance, not on direction, which means that many observers scattered through the large-scale cosmos would draw the same line through their local set of galaxies. No one needs to be at the center of anything. The linearity arises from the uniform growth of the scale factor across each slice of cosmic time, and from the near homogeneity of the matter distribution when smoothed over large volumes. This is why the relation appears as a mutual statement. Two remote observers riding with the flow each find the other carried away by the same rule, and no contradiction or privilege emerges. The relation is not a promise that nothing else matters. On very small distances, local gravity dominates, and the motion of galaxies inside groups and clusters does not follow the linear law. On very large look-back times, the relation bends as just described. Between these extremes lies the regime in which the linear form is not only visible but useful, because it connects redshift and distance in a way that is nearly model-independent. In that regime, the value of the slope is a compact summary of the present expansion rate that observers can compare as methods improve. The appearance of the relation in plots and maps encourages a final point about language. It is natural to speak of the recession rate of a galaxy at a given distance, and that wording invites the image of motion through space. The metric account remains the safer language. The rate is a measure of how quickly the proper distance between two comoving markers grows at the present time. A galaxy that sits on one marker and an observer that sits on another see their separation change at a rate that is proportional to their distance, and the light that passes between them records the cumulative history of that change. The straight line on the plot is a visual summary of this local rule. It does not imply that the galaxies are flying through a static void. It implies that the rule for distance inside the geometry changes in a uniform way across space at the present epoch. With this understanding, the Hubble-Lemaitre relation ceases to be a curiosity of early plots and becomes a foundational tool. It provides the first clear rung in moving from description to inference because it anchors the present rate of expansion in data. It sets the scale for nearby cosmological distances. It offers a baseline against which departures at higher redshift are measured departures that reveal the acceleration or deceleration of the scale factor through time. In short, it is the calm linear edge of a larger curve, a measured doorway from which the rest of the expansion history can be entered and traced. The distance ladder is a quiet architecture that links nearby geometry to the far reaches of the observable universe, through a series of overlapping methods, each one calibrated against those that come before it, and checked by those that run alongside it. At the base is parallax, the most direct rung. As Earth moves around the Sun, nearby stars trace tiny angular loops against the distant background. The size of the loop, measured in fractions that demand careful instrumentation, gives us geometric distance that does not rely on the intrinsic brightness of the star. Space observatories that measure positions with great precision have expanded this parallax foundation to many thousands of stars, tightening the 0 point for the rungs that sit above. From this geometric baseline, the ladder steps to pulsating stars whose periods and true luminosities are linked by a law first noticed more than a century ago. These are variable stars that brighten and dim with a regular beat set by their internal structure. When their period is measured, their true luminosity can be inferred, and the difference between true and apparent brightness gives a distance. Because some of these pulsators also have measured parallaxes, the relation between period and luminosity can be anchored without circular reasoning. Careful work then accounts for how chemical composition and crowding in distant galaxies might slightly shift the relation using observations in several colors to correct for dust that dims and reddens light along the line of sight. With this rung set, galaxies that host many such pulsators become distance anchors beyond the reach of simple parallax. A complementary rung uses the tip of the red giant branch, a point on a star's evolutionary path, where a sharp cutoff in brightness appears for old low-mass stars. The cutoff has a nearly universal luminosity with only mild dependence on composition. In galaxies where individual stars can be resolved, the sudden drop in the star count above this tip marks a standard candle. Because some galaxies host both pulsating stars and a well-measured tip, these two rungs can be cross-checked directly. Cross-checks matter because every rung carries sources of uncertainty that must be understood rather than ignored. Dust within the host galaxy or within the Milky Way can dim and redden light in ways that mimic distance. Blending of light from many stars in crowded regions can make a single source appear brighter than it is. Selection effects can creep in when only the brightest examples of a class are detected at great distances. Observers defend against these issues by observing in multiple bands to measure and correct for dust, by resolving crowded regions with sharp imaging, by building statistical models that include completeness limits, and by comparing results from independent rungs in the same galaxies. Another rung uses the slight graininess in the light of elliptical galaxies. If individual stars cannot be resolved, their random distribution still leaves small pixel-to-pixel fluctuations in brightness. The amplitude of these fluctuations depends on how far away the galaxy is, because distance smooths the star field. This method, called surface brightness. Fluctuations provides distances to galaxies too far for resolving individual stars, but close enough that the stellar populations are well understood. It too is tied back to galaxies that host pulsating stars, or a known tip of the red giant branch, so that its absolute scale is not floating. Spiral galaxies add a different tool. Their rotation speeds read from the breadth of their spectral lines correlate with their total luminosity. Faster rotating spirals tend to be brighter. This relation turns a rotation measurement into a distance estimate when calibrated in galaxies with known distances from lower rungs. Elliptical galaxies provide an analogous tool that connects their size's internal motions and surface brightness into a relation that yields distances once the 0 point is anchored. These empirical laws are not as precise per object as the best standard candles, but they apply to many galaxies and extend the ladder outward through numbers. A geometric jewel sits at still larger distances, where a few galaxies host thin disks of molecular gas very close to their central massive objects. The gas clouds act as microwave lasers, producing very bright narrow spectral lines. The orbits of those clouds can be mapped precisely, and the combination of angular motion across the sky and velocity along the line of sight yields a purely geometric distance to the host galaxy. Because such a system also hosts other indicators, it can serve as a strong anchor for the absolute calibration of brighter distance markers. This anchor avoids the need to pass through many intermediate steps, and therefore helps guard against slow drifts in the 0 point along the chain. The ladder then reaches for the brightest standardized candles that can be seen across a large fraction of the observable universe. Type Ia supernovae are stellar explosions, whose light curves follow a pattern that can be standardized. The brighter events decline more slowly after maximum light, and a combination of the light curve shape and the light color allows an estimate of the true peak luminosity. When many of these events are observed across a range of redshifts, they trace the relation between distance and redshift in a way that is sensitive to the time history of the scale factor. But their absolute scale, the step that turns a measured apparent brightness into a distance, depends on the 0 point set by the nearer rungs, such as pulsating stars, the tip of the red giant branch, and geometric anchors. Because supernova hosts sometimes also host these nearer indicators, the chain from parallax to pulsators to supernovae can be calibrated within the same galaxies, reducing the risk of hidden offsets. Alongside standard candles sit standard rulers. The most notable ruler for late-time distances is the preferred co-moving separation imprinted by sound waves in the hot plasma of the early universe, a scale that appears as a peak in the clustering of galaxies today. When that co-moving scale is known from early light and early physics, its apparent size at different redshifts yields distances that can be compared with those from standard candles. Although the ruler is covered in more detail elsewhere, it belongs in the ladder because it supplies a second independent route to distance as a function of redshift. Gravitational lensing time delays offer a further geometric handle. When a distant variable source is multiply imaged by an intervening mass, the light paths have different lengths and pass through different gravitational potentials. Variations in the source appear at different times in the multiple images. The measured delays, together with a model of the lens mass distribution and the geometry, provide a distance scale that does not rely on the brightness of any standard candle. A small but growing set of such systems offers cross-checks on the other rungs. Even newer are standard sirens, bright gravitational wave events from merging compact objects whose absolute amplitude follows from the theory of the waves. When such an event has an electromagnetic counterpart that provides a redshift, the pair supplies a distance without a classical candle. Though the sample remains small, the method illustrates how a ladder can gain new rungs that are grounded in different physics. The ladder rests on good practice as much as on instruments. Each rung is tied to others in the same galaxies whenever possible. Multi-wavelength data are used to control dust. Crowding is addressed by sharp imaging and careful modeling. Statistical methods incorporate selection effects rather than hoping they are small. The goal is not to pretend that each rung is perfect, but to make the uncertainties explicit and to ensure that different paths to the same distance scale agree within quoted errors. When they do, confidence grows that the distances placed on the redshift plot are not artifacts of one method, but a shared truth read by independent eyes. The practical outcome is that a galaxy with a measured redshift can be paired with a distance that carries a known uncertainty, and many such pairs reveal the local linear relation between recession rate and distance. As one looks farther, the same ladder extended by supernovae and rulers traces the bending of that relation that reflects the changing growth rate of the scale factor. Through this process, the ladder does not only supply numbers, it supplies a structure of checks that make the connection between light and geometry trustworthy. The result is a calm confidence that the expansion history read from the sky is a property of the universe rather than a mirage of methods, because many paths, each with its own careful steps, lead to the same long stair. Type Ia supernovae are bright stellar explosions that allow distances to be measured far beyond the reach of individual stars, and their measured pattern across redshift provides one of the clearest lines of evidence that the expansion of the universe has gently accelerated in recent cosmic time. The usefulness of these events rests on two linked facts. First, they're very luminous, so they can be seen across a large fraction of the observable universe. Second, their light curves, which show how brightness rises to a maximum and then declines, follow regular shapes that can be standardized. When this standardization is applied, and when careful corrections are made for color and for properties of the host galaxy, the peak brightness becomes a reliable yardstick. The combination of brightness, regularity, and standardization turns these explosions into distance markers that can be plotted against their redshifts to reveal how the relation between distance and redshift bends with look-back time. The path from explosion to distance begins with steady observation. Wide fields of sky are imaged repeatedly, and differences between images reveal new points of light in distant galaxies. Once a candidate appears, follow-up measurements record the rise to maximum light, and the subsequent decline over weeks and months. Spectra classify the event and measure the redshift by locating familiar atomic lines shifted to longer wavelengths. The classification matters because only a subset of stellar explosions follows the clean rules required for standardization. The type used for cosmology shows no hydrogen lines and displays features associated with intermediate mass elements near maximum light. These spectral signatures, together with the shape of the light curve, place the event into the class, whose peak brightness can be predicted once certain corrections are applied. A key empirical relation ties the width of the light curve to the true brightness. Events that fade more slowly after maximum are intrinsically brighter, and events that fade more quickly are intrinsically dimmer. A second correction comes from the color measured near maximum light, because redder events tend to be dimmed by dust along the line of sight, or by intrinsic differences that are handled with a common correction. These relations are calibrated using nearby explosions in galaxies whose distances are anchored by independent methods such as pulsating stars or the tip of the red giant branch. Once the relations are set, they can be applied to more distant events to infer their true peak brightness, and by comparing true brightness to observed brightness, a distance follows. Because the aim is precision, the analysis must confront several sources of systematic uncertainty. Dust within the host galaxy and within the Milky Way can scatter and absorb light in ways that vary with wavelength. Observers therefore measure the brightness in multiple bands and fit the entire light curve, rather than relying on a single point, allowing them to estimate how much dimming to attribute to dust and how much uncertainty to carry forward. Selection effects must also be handled with care. Surveys discover events above a detection threshold, which means that intrinsically brighter explosions are more likely to be found at greater distances, while dimmer examples may be missed. To avoid bias, survey strategies are modeled realistically, and statistical corrections are applied that account for the chance of finding events as a function of their brightness, color, and host environment. The goal is not to assume that selection effects are small, but to include them in the model from the start. Host galaxy properties enter as well. The stellar mass and star formation history of the host shows small correlations with the standardized peak brightness after the light curve width and color corrections are applied. Analysts therefore include an additional step that accounts for these host-related trends and then check whether any residual drift with host properties remains. Different light curve fitting methods and different training sets for those fitters are compared, and the spread among their results is folded into the uncertainty budget. With this suite of corrections and cross-checks in place, the standardized peak brightnesses become distances. When these distances are plotted against redshift, the nearby points trace the familiar straight relation that reflects the present-day expansion rate. As redshift increases and look-back time lengthens, the points depart from that straight line in a way that encodes the past growth of the scale factor. The critical observational finding is that distant standardized explosions are slightly dimmer than they would be if the scale factor had always been slowing its growth under the pull of matter alone. Dimmer at a fixed redshift means farther than expected on a purely decelerating history. Farther means that the scale factor must have grown more between emission and observation than the decelerating model predicts. The calm reading is that the late time expansion has gently accelerated. To convert this descriptive statement into a quantitative history, observers combine many events across a broad span of redshifts, from the nearby universe out to redshifts of order 1 and beyond. They then fit the full distance and redshift relation with a model in which the scale factor is driven by matter radiation and a nearly uniform energy density that does not thin as space expands. The fit shows that including such a uniform energy density explains the extra dimming of the distant events, while remaining consistent with the bright nearby points that anchor the present-day slope. The conclusion does not rest on a single survey or instrument. Independent teams have built samples using different strategies. Some scan large swaths of sky and trigger deeper follow-up on new discoveries. Others target known galaxies to increase efficiency. Some focus on the nearest events to refine the calibration by direct overlap with pulsating stars and with geometric anchors. Others push toward the highest redshifts with the largest telescopes to measure the bend of the diagram, where acceleration or deceleration leaves its mark. When these independent datasets are combined with careful attention to selection, calibration, and modeling, a consistent picture emerges. A further layer of confidence comes from agreement with probes that use different physics. The preferred co-moving separation imprinted by sound waves in the early plasma provides a standard ruler whose apparent size at several redshifts yields distances that match the same late-time acceleration. The pattern of temperature fluctuations in the cosmic microwave background, interpreted within the same large-scale geometric framework, selects parameters that, when projected forward, predict a late-time history in harmony with the supernova evidence. The agreement among candles, rulers, and early light gives the acceleration reading a stable base. None of this removes the need for continued care. Researchers test whether the empirical corrections for light curve shape, color, and host properties might evolve with redshift in ways that could mimic acceleration. They compare different light curve models and fitting codes. They ask whether dust in distant galaxies could differ systematically from dust nearby, and add near-infrared observations that are less sensitive to dust in order to reduce this worry. They examine whether selection effects might be more subtle than assumed and design surveys with well-understood cadence and depth to keep those effects under control. They refine the absolute scale by improving distances to the nearest calibrators with geometric methods, and by adding new anchors such as bright maser disks whose orbits yield distances without reliance on brightness. Through this cycle of measurement, correction, and cross-check, the distance and redshift relation drawn by standardized explosions retains its gentle bend, and the inference of late-time acceleration remains the calm reading of the data. In the narrative of expansion, these stellar explosions play a specific role. They extend the ladder to distances where the history of the scale factor can be read clearly. They trace the departure from a straight line that reveals how growth has changed with time. They provide a luminous, independent path to the conclusion that a nearly uniform energy density consistent with a cosmological constant dominates the recent expansion. Their value is not only that they are bright, but that their brightness can be placed on a common scale through observable properties, and that the remaining uncertainties can be treated with transparency. In this way, light curves become rulers, redshifts become timestamps, and together they write a measured chapter in the story of how the universe grows. Baryon acoustic oscillations provide a quiet standard ruler that links the physics of the early hot plasma to the pattern of galaxies seen today, and because this ruler has a nearly fixed length in co-moving coordinates, it allows distances to be measured without relying on the brightness of any object. In the first few 100,000 years after the hot dense beginning matter and radiation are tightly coupled, free electrons scatter light so frequently that photons and the ionized gas behave as a single fluid. Pressure in that fluid is set mainly by radiation, while inertia is set mainly by ordinary matter, and together they support sound waves that ripple outward from early tiny density seeds. Those waves travel at a predictable speed, close to 1 divided by the square root of 3 times the speed of light, because pressure and density have a simple relation in this hot-coupled medium. Each initial overdensity launches a spherical pressure wave that carries matter and light outward, while gravity tries to pull them inward. The dance between pressure and gravity sets up oscillations whose phases and amplitudes are determined by straightforward physics. As the cosmos expands and cools, neutral atoms form and light decouples from matter. Photons stream almost freely to become the cosmic microwave background, while the drag on the ordinary matter declines over a short but important interval sometimes called the drag epoch. When the drag fades, the outward moving shell of matter that had been riding the sound wave is left behind at a characteristic radius from the original seed. That radius measured in co-moving coordinates is roughly 150 megaparsecs a distance written here, in words to keep the calm style. It is the maximum distance the sound wave could have travelled before the coupling ended, and it becomes a preferred separation imprinted in the distribution of matter. 2 linked imprints remain. In the ancient light, the same sound physics appears as a pattern of peaks and troughs, in the angular power spectrum of the cosmic microwave background, with the first peak marking the scale of the sound horizon at decoupling. In the later distribution of galaxies, the same physics appears as a slight excess probability for pairs of galaxies to be separated by the sound horizon scale when measured in comoving units. The imprint in the galaxy distribution is not a sharp wall but a gentle bump in the 2-point correlation function, and a series of small wiggles in the power spectrum of clustering, because the underlying co-moving scale is set by early physics that can be modelled accurately, and is anchored by the cosmic microwave background. The apparent size of the feature at different redshifts provides a distance measure that reaches deep into cosmic time. The practical path from idea to distance begins with wide and deep galaxy surveys that map positions and redshifts for millions of galaxies. Angles on the sky give transverse separations, while redshifts provide radial positions after they are interpreted through an assumed expansion history. The preferred co-moving scale then appears as a weak ring in the correlation function, or as oscillations in the power spectrum. By comparing the apparent transverse size of the ring with its known comoving size, observers infer the angular diameter distance to the mean redshift of the sample. By comparing the apparent radial size of the ring along the line of sight with its known comoving size, they infer the expansion rate at that redshift. In this way, a single physical feature supplies both a distance across the sky and a distance along the line of sight, and together these measures constrain the scale factor history and the spatial curvature. The signal is small, so great care is taken to preserve and recover it. Nonlinear gravitational evolution and random motions of galaxies tend to blur the acoustic feature over time, smearing the sharpness of the ring. A technique called reconstruction partially reverses this smearing by using the observed large-scale density field to estimate and undo the displacements that structure growth has produced. After reconstruction, the acoustic bump grows sharper and the inferred distances become more precise. The method also benefits from the sheer size of modern surveys because the statistical noise declines when many independent patches of sky contribute to the measurement. Sources of systematic uncertainty are present but are different in character from those that affect standard candles. The overall bias between galaxies and the underlying matter affects the amplitude of clustering, but hardly shifts the position of the acoustic feature. Redshift space distortions from coherent flows and from small-scale random motions can stretch or compress the pattern along the line of sight. But these effects can be modelled and largely separated from the geometric scaling by their distinct angular dependence. The selection function of a survey which describes how the chance of including a galaxy varies across position and redshift must be measured and included so that artificial patterns are not mistaken for signal, because the ruler depends on a relative feature in the clustering and not on an absolute brightness. Many photometric calibration issues that challenge standard candles are not central here. All of these considerations are checked by repeating the measurement across subsamples, by comparing independent surveys, and by verifying that the inferred scale matches the one predicted by the cosmic microwave background when both are interpreted within the same overall geometric framework. The reach of the ruler extends beyond bright galaxies. At earlier times, when ordinary galaxies are fainter and harder to observe in large numbers, the forests of absorption lines imprinted on the light of distant quasars by intervening hydrogen clouds provide a way to sample the large-scale density field along many lines of sight. Correlations among those absorption patterns reveal the same preferred co-moving scale at redshifts of around 2 and beyond. The combination of galaxy clustering at lower redshifts and absorption forests at higher redshifts stitches together a continuous set of distance measurements that chart the expansion across most of cosmic history accessible to present instruments. The cumulative picture that emerges from these measurements is calm and consistent. The angular diameter distance and the radial expansion rate inferred from the acoustic ruler at several redshifts trace a curve of the scale factor that, when combined with the cosmic microwave background, points to a nearly flat spatial geometry and to a late-time acceleration consistent with the nearly uniform energy density of the vacuum. The agreement with the distance and redshift relation from standardized stellar explosions is not a coincidence. It is the mark of two independent methods, one based on calibrated brightness and one based on a fixed co-moving length, reading the same underlying geometry. Because the acoustic ruler is tied directly to early sound physics, and because that physics also sets the pattern of ancient light, the method locks the late universe to the early one in a single narrative. The acoustic ruler also supports purely geometric tests that do not rely on assumptions about how the intrinsic properties of galaxies change with time. By comparing the apparent size of the feature along and across the line of sight, observers can test for consistency between the angular diameter distance and the expansion rate. Any mismatch would signal either an incorrect assumed expansion history or a deviation from the simple curved but homogeneous and isotropic geometry. In practice, the measurements agree within quoted uncertainties, reinforcing the standard picture. Improvements continue steadily. Larger and deeper surveys increase the precision of the ruler. Better reconstruction methods recover more of the original sharpness. Multi-tracer analyses that combine different kinds of galaxies can reduce the noise caused by sample variance. Cross-correlations with weak gravitational lensing maps provide additional checks that the inferred distances are not biased by subtle observational effects. Even with such refinements, the conceptual meaning remains simple. The early universe sets a co-moving length by the distance that a sound wave can travel before light and matter decouple. That length leaves a faint preference in where galaxies tend to be a preference that survives to the present day after much growth and merging. By measuring how large that length appears at different redshifts, the geometry of space-time between emission and observation is read, and the history of the scale factor is traced. No outside medium is required. No motion through a fixed background needs to be imagined. A single scale birthed in an early plasma becomes a ruler that the universe carries quietly within itself, and by reading that ruler across time, the calm story told by expansion is confirmed and sharpened. The cosmic microwave background is a faint, nearly uniform glow of ancient light that fills the sky, and its gentle ripples in brightness and polarization provide some of the most precise anchors for the geometry and contents of the universe. This light last scattered from ordinary matter when the cosmos had cooled enough for electrons and protons to combine into neutral atoms, allowing photons to travel almost freely. That transition takes place when the scale factor was far smaller than today, and the photons have been stretched by the expansion ever since moving from visible and infrared wavelengths down to microwaves. Against this uniform glow, tiny temperature variations at the level of a few parts in 100,000 draw a detailed map of conditions on a vast spherical shell, centered on the observer, a shell often described as the surface of last scattering. The pattern on this shell is not random noise. It carries the imprint of the same sound waves that leave a preferred co-moving scale in the distribution of galaxies. Regions that were slightly overdense just before last scattering had matter and radiation compressed together, while neighboring regions were in a rarefaction phase. Pressure and gravity had been trading influence in a regular rhythm. When light decouples from matter, that rhythm is recorded as a standing pattern of hot and cold spots with a characteristic angular scale on the sky. The first prominent peak in the angular power spectrum of these temperature fluctuations corresponds to modes that have completed roughly half of a full oscillation by the time of decoupling. The angular size of that peak is set by a simple geometric rule: how large the sound horizon at last scattering appears when viewed from today, because the physical size of the sound horizon can be calculated from early plasma physics. With high confidence, the observed angular size turns into a clean measurement of the angular diameter distance to the surface of last scattering. That distance depends on the integrated growth of the scale factor and on the spatial curvature, so the peak location becomes a precise geometric anchor. If space is nearly flat, the first peak sits near an angular scale of about 1 degree. If space was strongly positively curved, the peak would shift to larger angular scales. If space was strongly negatively curved, the peak would shift to smaller angular scales. Observations show the peak very close to the flat prediction, with uncertainties small enough to constrain curvature tightly around zero when the data are interpreted within the homogeneous and isotropic model. The pattern does more than place a single peak. A series of peaks and troughs appears at higher spherical harmonic numbers corresponding to smaller angular scales. The relative heights of the odd and even peaks tell how much ordinary matter versus radiation was present, because ordinary matter deepens gravitational wells and shifts the balance between compression and rarefaction at the moment of last scattering. The overall envelope and the small-scale damping tail at very fine angular scales reveal the scattering history and the thickness of the last scattering surface, since random motions and diffusion smear out the tiniest features. Together, these details pin down the densities of ordinary matter and of all gravitating matter, the amplitude and scale dependence of the initial fluctuations and the angular diameter distance to last scattering with remarkable precision. Polarization adds a second independent map with different sensitivities. The scattering of light by free electrons generates a faint linear polarization pattern, whenever the incoming radiation carries a quadrupole anisotropy. The so-called even parity polarization pattern and the cross-correlation between temperature and polarization sharpen parameter inferences and help separate primordial signals from later effects. The odd parity polarization pattern on large angular scales would be a marker of gravitational waves from very early times if detected clearly, and although that search continues, the existing polarization maps already fix the integrated optical depth due to the later ionization of hydrogen by the first generations of stars and galaxies. That optical depth tells when the fog of free electrons reappears and partly rescattered the microwave background light, which subtly reduces power on large scales. Lensing of the cosmic microwave background by intervening large-scale structure provides another layer of information. As the ancient photons pass through clusters and filaments, their paths are deflected slightly by gravity. These deflections remap the patterns, smoothing the peaks and creating small non-Gaussian features that can be teased out with statistical tools. The reconstructed lensing map measures the projected mass distribution between us and the surface of last scattering and offers an independent handle on how structure has grown, which in turn depends on the expansion history and the contents of the universe. Because the cosmic microwave background arises so early, it sets an absolute yardstick that can be projected forward and compared with late-time probes. When the sound horizon inferred from the ancient light is matched to the preferred co-moving separation, measured in the clustering of galaxies, the two together calibrate distances across cosmic time. When the angular diameter distance to last scattering is combined with the late-time distances from standardized explosions and with the radial expansion rates from the acoustic ruler, the trio narrows the allowed histories of the scale factor and tightens the constraint on spatial curvature. The cosmic microwave background also checks the character of the initial fluctuations themselves. The data favor fluctuations that are almost but not exactly scale, invariant, that are nearly adiabatic, and that are very close to Gaussian in their statistics. These statements summarize how the variance of the temperature pattern changes with angular scale, and whether different regions fluctuate together across matter and radiation. Deviations from these simple properties would show up as shifts in peak positions, altered peak heights, or higher-order statistics in the maps. Within the precision of current measurements, the simple picture holds. Instruments and analysis must be as calm and careful as the conclusions. Foregrounds from our own galaxy, including emission from dust grains and from charged particles spiraling in magnetic fields, overlay the ancient light. Emission from distant galaxies and groups also contributes at small angular scales. Experiments therefore observe at multiple microwave frequencies because the spectrum of the ancient light is very close to an exact blackbody, while the spectra of foregrounds differ. By combining maps across many frequencies, the foregrounds can be modelled and subtracted statistically, and the residual uncertainties can be propagated into the error bars on the cosmic parameters. Precise knowledge of instrument beams, noise properties and scanning strategies is required so that small systematic effects are not mistaken for cosmic signals. Over the past decades, independent experiments using very different designs have produced consistent power spectra and maps, which strengthens confidence that the extracted features belong to the sky rather than to any one instrument. The cosmic microwave background therefore acts as a wide anchor with many tethers. It fixes the angular diameter distance to a very early surface, and thereby restricts the allowed spatial curvature. It sets the physical scale of the sound horizon that the late-time acoustic ruler uses. It measures the total amount of gravitating matter and the amount of ordinary matter separately, and it sets the initial conditions for structure growth. It records the integrated scattering from rhionization and maps the projected mass through lensing. When these strands are woven together, the picture that emerges is steady, a nearly flat large-scale geometry. A cosmic inventory dominated today by dark energy, consistent with a cosmological constant, and by non-luminous matter that interacts through gravity, and an expansion history that slows when matter dominates, and later gently accelerates. No outside into which the universe expands is required anywhere in this chain. The cosmic microwave background reads the geometry from within by using light that has travelled almost the whole way to us. Its peaks and troughs, its slight polarization, and its lensed wrinkles are all internal records of how distances and angles behave in the evolving metric. When those records are read alongside the distances from standardized explosions and the ruler written in the galaxy pattern, the calm agreement across methods becomes the main message. A single time-dependent scale and a nearly flat spatial geometry describe the measurements from the earliest map we can see to the latest maps we build. And in that shared description, the expansion acquires a precise observationally anchored meaning. The observable universe is a calm, precise idea tied to light and time, while the whole universe is the complete geometric stage that the model describes, whether or not any light has yet had time to reach an observer from all of it. The difference rests on horizons, which are boundaries drawn not by walls or edges, but by the finite age of the cosmos, and by the way the scale factor has grown. The first horizon is called the particle horizon. It marks the largest comoving distance from which light could have travelled to an observer since the early hot phase to the present moment. To define it, one imagines integrating the path of a light beam through the evolving geometry from the earliest times when the model still applies up to now. The result expressed in co-moving coordinates is a radius that encloses every region that has had time to send a signal that could arrive today. Because the scale factor was much smaller in the past, proper distances inside the comoving sphere were also much smaller then, and light could cross them more readily. As time passes, the particle horizon grows because more distant regions have time to send light that can reach the observer. The surface of last scattering where the cosmic microwave background formed lies well inside today's particle horizon. It is a thin shell from which ancient light reaches us now, and beyond it the particle horizon encloses regions whose light has not yet had time to arrive at microwave wavelengths, because earlier epochs were opaque. The second horizon is called the event horizon. It is defined with the opposite temporal viewpoint. Instead of asking what could have reached us by now, one asks what could ever reach us if the expansion continues according to the measured late-time behavior. One traces a light beam emitted now from a distant comoving location, and asks whether after travelling forward for an unlimited time that light will ever arrive. If it will not, then that comoving location lies beyond the event horizon. The existence and size of this horizon depends strongly on the late-time expansion history. In a cosmos whose expansion slows forever under matter alone, the event horizon would not exist, because any two locations separated by a finite comoving distance could in principle exchange light given enough time. In a cosmos with a sustained acceleration driven by a nearly uniform energy density of the vacuum, an event horizon appears because the scale factor grows so quickly that light emitted now from sufficiently distant comoving markers never makes up ground to reach us. This horizon does not fence off space in a mechanical sense. It records a limit on causal contact in the far future, set by the integrated growth of the scale factor. A third useful but different scale is the present Hubble length, defined as the distance at which the present proportional recession rate equals the speed of light. It is not a true horizon. Objects can lie beyond this length and still be observable because their light was emitted when they were closer and the scale factor was smaller. Likewise, objects within this length can become unobservable in the future if the scale factor grows quickly enough. The Hubble length is a snapshot scale related to the current expansion rate, whereas the particle and event horizons are integrals over time. The language of co-moving and proper distances helps make these distinctions precise. The particle horizon today is a comoving radius that increases with cosmic time. The proper distance to the particle horizon at the present moment is the current scale factor multiplied by that comoving radius. The event horizon today is the comoving radius beyond which events that occur now can never influence us, and its proper distance at the present moment is again the scale factor multiplied by that comoving radius. Because the scale factor changes, the proper sizes of both horizons change with time, even if their co-moving sizes follow different rules. The observable universe is therefore the region inside the present particle horizon. It is not centered on the Milky Way because of any special status, but because any observer anywhere would draw their own observable sphere centered on themselves, defined by the same rule that light has had only so much time to travel since the hot dense phase. Each observer's sphere encloses a different set of distant galaxies, but if the large-scale model is correct, each sphere looks statistically similar when smoothed over enough volume. The concept of an edge is not required. Beyond the particle horizon, there may be more of the same pattern that surveys reveal inside, or the topology could cause space to repeat in subtle ways, or the region could be infinite. Observations do not yet decide among all logically allowed options. What they do decide is the size of the observable sphere and the late-time behavior that likely creates an event horizon. The presence of horizons interacts gently with language about motion and about speeds. It is common to say that very distant galaxies recede from us faster than light, and this is not a violation of relativity in the metric view. The rate at which proper distance between two comoving markers changes can exceed the speed of light when their separation is large enough, because that rate is set by the growth of the scale factor across space rather than by motion through space. Light emitted toward us from a very distant galaxy can still arrive if it was emitted when the galaxy was within our particle horizon, and if the subsequent growth of the scale factor allows the light to surf inward through the evolving geometry. Whether that happens depends on the full-time history. In a future with sustained acceleration, there will be galaxies whose present light scent now will never arrive, because the event horizon lies between us and them in comoving coordinates. The image of a pass-like cone clarifies these ideas. One can picture at each moment a cone in space-time that narrows back from the observer's present event to earlier times, encompassing all events that could have sent signals that arrive now. The surface of last scattering is a slice through that cone where the ancient light last interacted with matter strongly and began to travel almost freely. The particle horizon is the boundary of that cone at the earliest times. In the forward direction, a future light cone widens from the present event, including all events that can be influenced by signals sent now. If a sustained acceleration continues, the future light cone fails to include comoving regions beyond a certain radius, which is another way of stating that an event horizon exists. Horizons also shape practical planning for observations. The particle horizon sets an absolute outer limit to what can be seen today by any means regardless of instrument power. Better telescopes reveal fainter sources and resolve smaller angles, but they do not move the horizon. The event horizon sets a limit on what signals sent now can ever influence. This matters for thought experiments about sending probes or receiving distant beacons. It also enters the calm understanding that some structures now visible will fade beyond causal contact in the far future if acceleration continues, not because they move through a medium to cross an edge, but because the geometry grows so that later light from them cannot overcome the stretching to reach us. The existence of horizons does not introduce any paradoxes about energy or information when read in the metric language. Energy conservation takes specialized forms in an expanding space-time, and the redshifting of photons is understood as part of the evolving geometry. Information that never arrives is not lost from a region where it was never present. Each observer's world line carries its own observable sphere that grows with time, and if acceleration endures, each world line also carries its own event horizon that fixes which distant events can ever be shared. Finally, the distinction between observable and whole universe helps answer the title question without invoking an outside. The observable sphere is bounded by the particle horizon because light and time are finite, and the event horizon may bound what can ever be influenced if acceleration continues. Neither boundary is an edge in space. They are limits in time and in signal reach within the same geometry. The whole universe, as far as the model is concerned, is the full manifold described by the same metric, possibly infinite and possibly finite without boundary, and the expansion is an intrinsic change in how distances are measured on that manifold. The calm reading is that what can be seen is set by horizons. What can ever be exchanged is set by horizons, and what exists in the model does not require an outside into which anything moves. Spatial curvature and global topology are the quiet background of cosmic mapping, because they define how straight lines behave and how space may wrap without edges. Curvature describes whether large triangles drawn by geodesics on a slice of constant cosmic time add to more than equal to or less than the familiar sum from school geometry. Global topology describes how that slice might connect to itself at the largest scales, allowing space to be finite without boundary or infinite, and allowing patterns to repeat in subtle ways. The Friedman-Lemaitre-Robertson-Walker model separates these ideas cleanly. At each cosmic time, the spatial geometry is homogeneous and isotropic, and only 3 curvature families are allowed by those symmetries. Positive curvature resembles the geometry on the surface of a sphere. Negative curvature resembles the geometry of a saddle, and zero curvature is flat. Within any one family, many topologies are possible. A flat space may extend without end, or it may repeat in one or more directions like a 3-dimensional generalization of a torus, so that traveling far enough returns an explorer to the starting point without crossing an edge. A positively curved space can be the 3-dimensional surface of a 4-dimensional sphere, which is finite without boundary, or it can be a quotient of that sphere by identifications that shorten or twist the path lengths. A negatively curved space can be infinite or constructed to be compact by careful identifications. The calm task of observation is to measure the curvature and to look for signs of a repeating topology, while keeping the 2 concepts distinct. Curvature influences measurements through the relation between angles, distances, and areas on each cosmic slice. If space is positively curved, then for a given physical size at a given distance, the observed angular size is larger than in a flat geometry. If space is negatively curved, the observed angular size is smaller. The cosmic microwave background provides a precise anchor because the physical size of the sound horizon at last scattering can be calculated from early plasma physics, and the observed angular scale of the first acoustic peak therefore becomes a sensitive probe of the angular diameter distance to that ancient surface. That distance in turn depends on the integrated growth of the scale factor and on spatial curvature. When the peak appears at the expected angular scale for flat space with small error bars, the inference is that the curvature is very close to zero. Late-time standard rulers and standard candles then sharpen the picture by fixing the expansion history between us and the ancient surface. Together, these measurements confine curvature to values near flat within the uncertainties which themselves have steadily narrowed as maps and catalogues have improved. Topology leaves different kinds of signs. If space repeats, the larger scale patterns can imprint repeated features on the sky. The most famous example is the search for matched circles in the cosmic microwave background. If the last scattering surface intersects itself because space wraps around, then the observer could see the same region of that surface in different directions, producing pairs of circles with identical patterns of temperature fluctuations. The search scans the microwave background map for such pairs, allowing for possible twists and rotations implied by different identifications. No convincing matched circle pairs have been found at the sensitivity of current maps, which constrains many repeating topologies out to scales comparable to or larger than the radius of the observable sphere. Another sign would be a suppression of power on the very largest angular scales if the fundamental domain of the topology is too small to contain modes longer than that domain. The observed large-scale power is low in some channels, but not in the coherent way that a compact simple topology would demand, and the full pattern of peaks and troughs across many angular scales remains well described without invoking such a cutoff. Galaxy surveys and three-dimensional maps add a complementary route. If space repeats within the observable volume, distant structures may appear more than once in different directions, with consistent redshifts and morphologies. Analysts have looked for such multiple images of large clusters or distinctive features, allowing for the possible distortions introduced by projection and by growth over look-back time. No robust repeating pattern has been confirmed. The absence of such signatures within current sensitivity does not prove that space is infinite. It shows that if space repeats, the characteristic size of the repeating cell likely exceeds the present observable radius by a comfortable factor. The distinction between curvature and topology matters for language that answers the title question. A positively curved space can be finite without boundary, like the surface of a sphere extended to 3 dimensions, and it needs no outside into which it curves. A flat space can also be finite without boundary if it repeats again without any outside. An infinite space can be flat or negatively curved. In every case, the expansion is the intrinsic change of the scale factor that multiplies spatial distances on each slice. Whether space is finite or infinite in extent, the metric defines distances within the space itself. The rules that tie angles, areas, and luminosities to distance follow from that metric, and a light travels along paths within the same geometry. Observers often ask how tightly curvature is known. The answer comes in careful words. The position of the first acoustic peak in the cosmic microwave background and the full pattern of peaks together with late-time distances from the acoustic ruler and galaxy clustering and from standardized stellar explosions restrict the mean curvature across the observable volume to be very small, with error bars that shrink as data sets grow. The statement is statistical and applies to the region we can map. It does not claim that the mean curvature everywhere in the whole universe is exactly zero, only that within the observable sphere any departure from flatness is smaller than the present sensitivity can detect, once the expansion history is included consistently. This already has practical consequences. When curvature is near zero, different cosmological distance measures relate to redshift, in ways that are pinned down predominantly by the expansion history rather than by geometric bending. This simplifies combined fits and reduces degeneracies among parameters. When curvature is allowed to float within its small allowed range, the constraints on the late-time acceleration remain stable. Topology constraints, while less sharp than curvature constraints, also carry practical meaning. The absence of matched circles at current sensitivity implies that if space repeats, the smallest closed path that returns to its starting point must be larger than the diameter of the last scattering surface, by a factor that depends on the specific identification. This fact quiets simple pictures in which a small torus would produce many obvious repeats in the sky. The sky does not show such repeats. More exotic identifications with twists or with anisotropic fundamental domains are not fully ruled out, but they face similar tests, and the bar for evidence remains high. The measurement program continues with the same calm approach used throughout cosmology. Better maps of the microwave background, especially in polarization, can push the search for matched circles and for subtle topology signatures to finer levels. Larger galaxy surveys that cover more of the sky and reach to higher redshift can widen the search for repeated structures and tighten the combination of distances that fixes curvature. Weak lensing maps that measure the shear pattern of background galaxies add geometric information that also depends on curvature and cross-correlations among microwave background lensing galaxy clustering, and shear increase the leverage on the larger scale geometry. Even without decisive new signatures, the present conclusion is meaningful. The large-scale universe within the observable sphere behaves as if its spatial slices are very close to flat. No repeating topology is seen within current sensitivity. Finite without boundary remains allowed in principle if the repeating cell is much larger than what we can see, and infinite extent remains allowed within the same precision. None of these options requires or even admits an outside space to expand into. The expansion is the steady change of the scale that turns co-moving labels into proper distances. Light reads that change through redshifts, angles and brightness. Curvature controls how those angles and areas behave, and topology controls whether the largest patterns repeat. The data so far say that curvature is small, and that repetition, if present at all, lies beyond reach. The geometry is therefore calm and simple on the larger scales we can probe, and the language that follows from this geometry continues to answer the title question from within the universe, expands by changing its internal ruler across a space that is nearly flat, and may be either very large and finite without edges, or truly infinite with no requirement for any outside into which it grows. Dark energy enters the calm narrative as the name for whatever causes the late-time expansion of the universe to accelerate rather than to slow under the pull of matter. The simplest candidate is the cosmological constant, a uniform energy density that fills space evenly and does not dilute as the scale factor grows. In the equations that tie geometry to contents, such a constant acts like a pressure that is negative enough to drive acceleration. The measured relation between distance and redshift for standardized stellar explosions. The preferred co-moving ruler imprinted by early sound waves and read in galaxy surveys, and the angular pattern of ancient light when projected through the later geometry, all align with the history in which after matter has dominated, a nearly uniform energy density comes to dominate and turns a slowing expansion into a gently accelerating one. The cosmological constant has two quiet properties that match this picture. First, its energy density remains nearly the same as the universe expands, so its relative share of the total energy rises as matter thins with the growth of the scale factor. Second, its pressure is negative with a ratio of pressure to energy density very close to -1, which is precisely what produces acceleration in the smooth equations of the large-scale model. Observers do not measure this ratio directly with a single device. They infer it by fitting the full pattern of distances and by checking how structure has grown over time, since a stronger or weaker negative pressure would lead to a different bending of the distance and redshift relation, and to a different pace in the clumping of matter. Within current precision, the best fits select a pressure to energy ratio close to -1, and a constant in time which is the signature of the cosmological constant. The calm agreement among methods does not end the conversation. More flexible possibilities remain allowed within quoted uncertainties, and they motivate continued work. One class of alternatives treats dark energy as a new smooth component whose energy density and pressure can change slowly with time, sometimes called a rolling or dynamical field. If such a component drives acceleration, its ratio of pressure to energy density could deviate slightly from -1 and could drift with redshift. The component would also tend not to clump on small scales the way matter does if its internal sound speed is high, which would leave a distinct imprint on the growth rate of structure. Another class of ideas changes the way gravity behaves on the larger scales, adjusting the link between geometry and contents rather than adding a new energy component. In those models, the same light-based distance relations might be reproduced, but the growth of clustering could differ because the pull that drives matter into filaments and clusters would have a different time and scale dependence. The observational program therefore tests dark energy with two complementary themes. The first theme is geometry. Distances across the sky and along the line of sight are read with rulers and candles at many redshifts, and their pattern is compared with the curves that a constant or a slowly changing negative pressure would draw. The second theme is growth. Maps of galaxy clustering weak gravitational lensing that traces the small distortions in the shapes of distant galaxies by intervening mass and the lensing of ancient light combined to measure how the amplitude of matter fluctuations has increased over time. By comparing geometry and growth, one asks whether a single smooth negative pressure in the standard gravity framework explains both, or whether a more complex explanation is required. So far, the quiet summary is that a constant negative pressure fits both geometry and growth within uncertainties across the redshift range that current surveys probe. Even with this agreement, several conceptual questions remain. The first is why the energy density of the constant should take the tiny value that measurements imply when written in the same units that describe particle physics, where naive estimates of vacuum energy are far larger. This is sometimes called a problem of magnitude. The second is why we live at a time when the energy densities of matter and of the constant are of the same order, given that one thins with expansion and the other does not. This is sometimes described as a problem of timing. Cosmology alone does not supply answers to these questions. The calm stance is to treat the constant as a parameter that observations measure, and to keep searching for additional clues that might point to a deeper explanation, either in the physics of fields and vacua or in the behavior of gravity on very large scales. Precision also matters for a practical reason. Small deviations from a constant pressure to energy ratio could be the first signs of richer dynamics, but they could also arise from unnoticed systematic errors in one or more probes. The strategy to guard against this is the same one used throughout the narrative. Build multiple independent measurements with different instruments and different methods. Compare distances from stellar explosions with distances from the acoustic ruler, and with the angular diameter distance to the ancient light. Compare growth inferred from galaxy clustering with growth inferred from lensing of galaxies and of ancient light, improve control of nuisances such as dust calibration and selection in each probe. Where methods overlap in redshift and in sky coverage correlate the maps so that shared structures act as a common reference and hidden biases come into view. This web of cross-checks turns a single parameter into a measured part of a wider network of facts. The presence of a constant negative pressure also affects expectations for the far future. If the constant remains dominant and unchanging, the scale factor continues to grow in a way that causes distant comoving regions to slip beyond each other's event horizons. Structures that are not bound by their own gravity drift out of causal contact as later light from them fails to reach us, leaving bound islands such as galaxies and smaller systems as the long-term, slowly dimming stage. This consequence does not answer why the constant should exist, but it clarifies what the same measured parameter would mean if it keeps the same value. Alternatives with slowly changing pressure to energy ratio would alter this future, either making the acceleration stronger or weaker. With time and the growth of structure observed today sets limits on how much such changes can occur, without contradicting the lensing and clustering data. Some speculative models that once offered dramatic endings are already constrained strongly by the combined data. In the present, the discipline remains to speak in measured words. The late-time acceleration is robustly inferred from distances that bend away from a matter only slowing history. A nearly uniform energy density that does not dilute and that exerts negative pressure provides the most economical fit. The ratio of pressure to energy density consistent with -1 within current uncertainties is the concise way to state this fit, although the statement can be made without symbols by saying that the pressure is as negative as the energy density is positive. Alternatives that vary slowly with time are allowed but bounded by geometry and by the observed pace of clustering. Modifications of gravity on the larger scales are also bounded by the match between geometry and growth, and by the lensing of ancient light which measures directly how mass bends the paths of photons. None of these empirical statements require invoking an outside into which space expands. They are features of the internal rule for distance and time and of how that rule changes. In this sense, dark energy is not a substance poured into a container, but a description of how the cosmic ruler evolves. The cosmological constant is the calmest form of that description, fitting the present data with the fewest moving parts. Whether that calm simplicity signals a deep truth or a temporary affective picture is an open question that further measurements will explore. But in the narrative so far, the constant serves as the measured bridge between the bending of the distance and redshift relation, and the gentle acceleration that the large-scale universe displays. Analogies help turn abstract geometry into pictures that can be held in the mind, but they must be used with care so that they clarify rather than mislead. The balloon surface is a familiar image. Dots or small coins on a rubber balloon move farther apart as the balloon is gently inflated, and no single dot sits at a special center on the surface. This picture captures two useful ideas. First, it shows how all separations can grow at once without any one point being privileged. Second, it shows how something can be finite, yet without an edge, because the surface of a sphere is finite in area, and yet an ant can walk forever without encountering a border. The limits of the picture arrive just as quickly. The surface is two-dimensional, while the real spatial slices of the universe are three-dimensional. The balloon expands into an outside room filled with air, while the large-scale spatial slices in the model do not expand into anything external. The coins may slide or stretch relative to the rubber depending on how they are glued, which confuses the point that bound systems do not expand with the scale factor, whereas the surface itself does. The exercise therefore helps when it is used to illustrate the uniform growth of separations and the lack of a special centre, and it misleads when it tempts one to ask what lies outside, or to imagine that galaxies are stretching rubbery bodies. A calmer refinement replaces coins with dots of ink painted on the surface and then dried so that they do not stretch, making the point that bound structures resist the overall expansion. Even then, the need for an outside remains an artifact of the picture, not a feature of the geometry. The raisin bread image offers a second, slightly different view. A loaf of dough dotted with raisins is placed in a warm oven. As the dough rises uniformly, the raisins move away from one another, and the more distant raisins move away faster, because there is more dough between them to rise. This captures the proportionality between separation and apparent recession rate that the Hubble-Lemaitre relation describes in the nearby universe, and it does so without suggesting a curved surface. Again, the limits are clear. The dough expands into the oven, which serves as an outside. The loaf has a crust, which is an edge. Real galaxies are not raisins carried passively by a uniform medium. They are concentrations of matter embedded in a metric that changes. The analogy clarifies the idea that a uniform growth rate creates velocities that rise with distance, but it should not be pushed beyond that calm lesson. A third, quieter picture uses a coordinate grid drawn on an elastic sheet. The grid spacing stretches uniformly as the sheet is gently pulled, while rigid washers placed at a few intersections are held together with stiff glue so that they do not expand. This shows how co-moving labels stay fixed while proper distances grow, and how bound objects keep their sizes even as the grid spacing increases. Once more, the outside hands pulling the sheet are not a part of the real story. They are only the human mechanism that produces the stretch in the analogy. In all of these pictures, the shared danger is that a helpful visual for uniform growth can be mistaken for a mechanical model. Metric expansion is not pressure pushing into an outside. It is the time dependence of the rule by which distances are measured between comoving markers, a rule that is fully internal to the geometry. The safest way to speak is to borrow what is useful and to discard what is not. From the balloon, keep the lack of a special centre and the possibility of finite without boundary. Discard the outside air. From the raisin bread, keep the proportionality of apparent recession rate to distance. Discard the crust and the pan that holds the loaf. From the elastic grid, keep the distinction between co-moving labels and proper distances and the immunity of bound systems. Discard the pulling hands. Analogies also stumble around speeds and horizons. The balloon and the loaf can suggest that nothing can separate faster than light, because the dots and raisins are carried by material media with ordinary elastic properties. In the metric account, the rate at which proper distance grows between two very distant comoving markers can exceed the speed of light without any violation of relativity, because this rate is not a local speed through space, but a measure of how the scale factor changes across the space between them. A better way to avoid confusion is to connect speed statements to local measurements only, and to return to light paths and horizons for global questions. Light emitted by a distant galaxy long ago can still reach us today, even if the proper distance between us and that galaxy now grows faster than light, because the key is whether the light was emitted inside our past light cone, and whether the integrated growth of the scale factor allows the beam to make headway through the evolving geometry. This clarity cannot be packed into a raisin or a balloon without words that explain it. Analogies also blur the difference between curvature and topology. The balloon surface is curved and finite, but real spatial slices may be very close to flat and either infinite or finite without boundary depending on topology. Someone who sees only the balloon may come away thinking that expansion requires positive curvature, The calm correction is to say that expansion depends on the time dependence of the scale factor, while curvature tells how angles add in large triangles and topology tells how space might repeat. A flat three-dimensional slice can expand uniformly with the same clarity as the balloon surface expands, and it can be either infinite or finite without boundary, depending on whether it repeats neither case requiring an outside. Another frequent trouble appears when the pictures are used to imagine the early hot dense phase. A balloon pressed down to a point looks like a bomb ready to burst, and seems to suggest a special place where everything began. The uniformity seen in the cosmic microwave background and the calm language of the Friedman-Lemaitre-Robertson-Walker model speak differently. The early phase is not an explosion from a center into emptiness. It is a time when the scale factor is small, and growing the matter and radiation density are high, and the whole spatial slice carries these properties everywhere at once within the observable domain. No analogy that starts from a single point in a surrounding space will carry that meaning faithfully without careful words to repair it. Because of these limits, the measured anchors deserve to stand beside any picture used to teach. The cosmic microwave background fixes a standard angular scale. The preferred comoving separation in galaxy clustering fixes a standard length. The standardized light curves of certain explosions fix a distance scale when calibrated. These are not analogies. They are the ways light writes geometry into data. When a picture creates confusion, the remedy is to return to these anchors, write the relations in plain language, and remind that the change described is the internal change of a metric. Used sparingly and framed with their limits, analogies can still play a helpful role. They lower the threshold for entering a subject whose natural language is geometry and differential relations. They offer images for uniform growth without a special center for finite, without boundary, for the difference between labels that ride with the flow and distances that change. They can point toward the right questions, such as how rulers and clocks behave, and how light records those behaviors across time. But they cannot answer those questions on their own, and they must yield the stage to definitions whenever they tempt the mind toward an outside container, a crust, a mechanical pressure, or a hidden center. In the calm narrative of expansion, the correct picture is the one that treats space and time together as a single fabric, whose rules change with co-moving labels that stand still, while proper distances grow with light that stretches in step with the fabric and with geometry that can be nearly flat and either finite without edges or unbounded without needing any beyond. The title's question asks what the universe expands into, and the calm answer is that in the standard large-scale model, there is no outside that plays any physical role. Expansion is an intrinsic change in the metric, the rule that turns co-moving separations into proper distances on each slice of cosmic time. The scale factor grows co-moving labels stay fixed, and proper distances between those labels increase. Nothing moves through an external medium, nothing crosses an edge. The geometry itself evolves and light records that evolution. Language invites a picture of an outside because everyday growth in familiar settings involves containers, surfaces and surroundings. A rising loaf needs an oven. A swelling balloon needs a room. A river needs banks. The universe in the model used to interpret data is not a material object set inside a larger pre-existing space. It is the entire stage described by a manifold and a metric, which together specify which events are near or far, which intervals are spatial or temporal, and how clocks and rulers behave. Asking for the outside of that stage is like asking for the north of the North Pole in the specific geometry of Earth's surface. The question acquires force from daily intuition, but it does not have a target within the model. This does not forbid mathematical embeddings. One can represent a curved two-dimensional surface as living inside a three-dimensional space to help visualization, and one can imagine higher dimensional embeddings for three-dimensional spatial slices. Those embeddings are tools of thought. The extra space in which the picture is drawn has no measured effect. The physics is fixed by distances and times measured within the geometry itself, not by coordinates of a surrounding construction. Intrinsic curvature which the model uses is defined and measured entirely from within by how geodesics behave and how angles add in triangles drawn by those geodesics. Extrinsic curvature which an embedding picture might display is not what observations read. The distinction between inside and outside also becomes clear in the way coordinates can be chosen. The same space-time can be covered by many coordinate systems, some of which make the large-scale expansion explicit, and some of which hide it. A familiar example is an empty model with negative spatial curvature, in which one set of coordinates makes the expansion look like a steady increase of the scale factor, while another set of coordinates maps the same space-time into a region of flat Minkowski space in which there is no global expansion at all. The galaxies that ride with the flow are then described as moving apart through a static background in one coordinate choice, or as staying at fixed co-moving labels while the metric grows in another. Neither view is more real. The physical content is in statements that do not change under a change of coordinates. Light from distant sources is stretched by the same ratio that the scale factor grows between emission and observation. Large triangles on spatial slices have angle sums that reflect the intrinsic curvature. The particle and event horizons are defined by integrals of light paths through the geometry. The freedom to choose coordinates without altering those statements shows why an imagined outside is not part of the measured story. A second source of outside language is the image of an edge that expansion might approach. In the model, no such edge is required. Spatial slices can be infinite or finite without boundary depending on topology, and in both cases the metric evolves everywhere on the slice without reference to an exterior. Finite without boundary can be pictured by the two-dimensional surface of a sphere where a traveller may walk forever without meeting a rim. In the three-dimensional case, the exact shapes cannot be drawn in everyday space, but the same idea holds the path can be closed without a wall. If the slice's infinite expansion stretches all comoving separations and leaves no preferred centre within the slice. If the slice repeats, expansion stretches the repeating cell as well, and no crust appears. An edge would be an extra assumption not demanded by observation. A third motif behind the title's question is the creation of new space. The phrase is an attempt to capture that proper distances grow even between comoving markers that do not move through space. It can be helpful if it is kept modest. It should not suggest that space is a substance extruded from somewhere into an outside. The measured facts are that the scale factor grows that light wavelengths stretch in step with that growth, and that comoving volumes at later cosmic times hold more proper volume than the same comoving labels did earlier. Whether one says that more space exists between the labels, or that the labels are farther apart because the metric has changed, is a choice of words, not a difference in physics. Energy language adds a final pressure toward an outside. If photons lose energy by redshifting, one might ask where that energy goes, as if a container outside might collect it. Energy conservation in general relativity is subtle and local. In a static spacetime with a time translation symmetry, a global energy can be defined and conserved. In a spacetime whose metric changes with time, no exact global energy exists that applies to the whole slice, and the redshifting of photons is not a transfer into a reservoir. Locally, energy and momentum are conserved in the precise sense given by the equations that tie geometry to contents. Globally, there is no single number that must remain fixed when the ruler itself evolves. The calm way to state this is that the redshift is a geometric effect, not an exchange with an outside. Horizons give the question a last twist by seeming to draw a boundary that light crosses into or out of. The particle horizon marks how far signals could have reached by now, and the event horizon, if acceleration continues, marks how far signals sent now can ever reach. Neither horizon is an edge in space. Both are limits in time and in causal contact defined by integrated light paths within the geometry. A galaxy beyond the event horizon is not outside the universe. It is a commoving region with which communication sent now will never be completed in the future if the measured acceleration endures. The same geometry that defines those horizons defines the ruler that expands the angles that encode curvature and the distances that candles and rulers measure. No step in this chain appeals to an external arena. The standard model answers the title by turning the question inward. It says define co-moving labels that follow the average flow, define a scale factor that multiplies spatial distances on each slice of cosmic time, measure how that factor changes with time using light from standardized explosions, the preferred commoving separation written into clustering, and the ancient light that fixes an early yardstick and an early distance. With those definitions and those measurements, the universe expands by changing its internal ruler. Where the ruler acts spaces, where light travels the map is drawn. Where horizons limit reach, the limits are of time and of signal, not of walls. If topology makes the slice finite without boundary walking, forever returns to a starting point without an exit. If topology leaves it infinite, walking forever never ends, and still meets no outside. In both cases, the model remains complete without an external volume to grow into. The proper distancing from pictures that require an outside is therefore not a refusal to visualize. It is an invitation to use pictures that respect the measured anchors. One may imagine a grid that stretches a ruler that lengthens between marks, and a wave whose crests are carried apart by that same stretch. One may imagine clocks that ride the average flow and tick, cosmic time, and light cones that bound what is seen and what can be signaled. These images live wholly within the geometry. They leave no gap that an outside must fill. When a picture tempts an outside, the remedy is to return to the definition of the metric and to the facts that read it. The expansion into anything is not part of the story that observations support. The change of the scale that defines distance is the story, and that story is enough to explain the maps of redshift and distance, the rings of preferred separation in galaxy surveys, and the peaks in ancient light. In this calm sense, the universe expands into itself, because the expansion is the evolution of the very rule by which its within is measured.